I want to start collecting my work on this YouTube channel, and I thought the best way to do this would be by starting with my master's project. This project is about photoevaporation of red giant stars, and it will investigate whether the phenomenon of photoevaporation can explain why some of these stars are missing at the center of the galaxy. We know that stars in a gravitational potential, by interacting gravitationally with each other, will slowly drive themselves into an equilibrium distribution. This is called a cusp distribution, and it is what is shown in yellow in this plot. However, this does not happen for red giant stars. Closer to the center, their distribution flattens out, and this indicates that some of red giants are missing. Different mechanisms have been proposed for why these stars are missing, and the main approach is investigate the hypothesis that these stars are actually there, but we cannot see them. Red giants are stars that form when stars like the Sun exhaust most of their fuel and they balloon in size, so they're relatively light and not too dense. This means that the material at the outer edges of the star is in a very shallow gravitational potential, and it can be stripped pretty easily. Plus, they have a very large cross-section, and so collisions are a very relevant mechanism through which they can lose this outer layer. And losing this outer layer means that the radius of the star will reduce quite a lot, since the luminosity is roughly proportional to the radius. This means that it will become much harder to detect. There have been two approaches that consider collisions. One, consider collisions with other stars or stellar mass black holes, and the other, collision with a disk of material that is present in the central region of the galaxy. Other approaches instead investigated interactions with a central black hole in the galaxy, the supermassive black hole Sagittarius A. The first is based on the idea of tidal stripping, which happens to stars that get too close to the supermassive black hole. They will be torn apart by the tidal forces experienced when being this close to this massive object. The other proposal is that jet activity from the black hole itself would strip the stars from the outer layers. This happens because we know that objects like quasars can emit intense jet of radiation from their poles, and this radiation can basically strip away all the layers of the star. The authors of this last paper note that it's likely that all of these mechanisms together contribute to the observed lack of red giants, as each of them on their own fails to fully account for the missing stars. And so it's likely there will be a region in which the tidal stripping is important, and then a bit further away, the ablation because of jets and collision with black holes will become more relevant, and then later collisions with other stars and with the disk. Our proposal is that photoevaporation can also strip the stars of their envelope and perhaps help complete this picture. But to do this, we have first to assume that there was past activity from the central supermassive black hole, and we have evidence of this in the form of the Fermi bubbles. These are massive bubbles of X and gamma rays that extend in the direction perpendicular to the plane of the galaxy, and by tracing them back, we know that the event that generated them happened roughly 10 million years ago. We have simulations of jets of material emitted from the black hole that agree that Fermi bubbles can be formed in this way, and they agree on a timescale of a few million years. So we know that the last activity from the black hole was roughly a few million years ago. We know that the activity of a black hole is always linked to the presence of an accretion disk. This is a disk of material that is falling towards the black hole, and the only way the material can get closer is by losing energy, and it does this by interacting with the surrounding material, and it's dispersing its energy in the form of heat, which means it will heat up and emit radiation. Our idea is that the radiation will be energetic enough to ionize hydrogen, and it will deposit energy in the outer region of the star, since most of the star is made out of hydrogen. It will do this until all of it is spent and the fraction of ionized hydrogen drops to zero. This will create a very thin region in which this fraction is drastically lowering, and all the gas behind it will stay still and not feel anything. But the gas that was bathed in radiation will gain a lot of energy and be able to escape the gravitational pull of the star and be lost in the form of what we call a Parker wind. Our calculations will involve verifying that the spectrum of the black hole has indeed the right properties to be able to do this. Next, we will calculate the position of the base of the flow, the ionization front, and use it to calculate the rate at which the star loses mass. This will depend on the parameters of the star, specifically its mass and radius. And last, we will solve the model of stellar structure that will be used to determine how the star will evolve while it's losing mass. This is our calculation for the spectrum of the accretion disk. This shows the amount of radiation emitted in different frequencies, and what is important here is that the vast majority of the radiation happens at these frequencies here, which are above 13.6 electron volts. This means that there is enough energy in each of the photons of these frequencies to be able to knock out an electron from a hydrogen atom. And to calculate the spectrum here, we assume that each concentric ring of the accretion disk was at a certain temperature given by this effective temperature profile calculated by estimating how much energy the material needs to lose to get at that distance from the black hole. Then we sum the black body spectrum for each ring to obtain this final spectrum. Next, we calculated the position of the ionization front, which is the base of the flow, the point from which the stellar wind starts. And this is perhaps a bit technical, but basically what we did was assuming that the fluid behind it wasn't moving, and that way we could find the gap in the density profile from the fact that the fluid on this side is still and the fluid on the other side is moving. And by that, we can then use this density profile to estimate the number density of hydrogen and calculate how the fraction of ionized hydrogen behaves as the radiation gets closer to the star. And it should go to zero at the position of the ionization front. But if it doesn't do that, then it means that that position that we chose at the start is not the correct position. So we have to tweak the position of the ionization front until it matches in these two calculations. And that means that for the mass and radius that we chose to solve this model for, that position is the correct solution. And from there, we can actually find the rate at which mass is lost because of our knowledge of the density and velocity at a certain position. This formula allows us to find this mass loss rate. And now the plot shows the obtained result. The color is the logarithm of the mass loss rate in solar masses per year, while the x-axis we have the mass, and on the y-axis we have the radius. This white line is separating this parameter space of all possible stars into regions, one in which the stars take less than 3 million years to evaporate, and one in which they take more than 3 million years. This then means that some evaporation can happen, specifically of the stars in this region. The problem is that just from this plot, it is hard to tell how long this evaporation will last. What if the star loses a little mass and then it quickly moves down here where it gets stuck? We need some way to see how the star evolves under this photoevaporative process. This is the stellar structure model we use. Our basic assumptions are that the star is a star in the red giant branch, which is just a standard red giant. It has a core which contains helium, which is all the spent fuel that it burned during its life as a main sequence star, like the Sun. And then there's a thin shell of hydrogen that is still undergoing nuclear fusion outside of it, which is surrounded by an envelope dominated by convection. Convection drives the temperature profile very close to adiabatic, which means that the temperature profile will look like that of a gas in which no heat is being exchanged. And then by simply assuming hydrostatic equilibrium, we can solve this model to find the star radius for a given core and star mass. That way we can use this to find the new radius of a star after we shave off some of its mass. For the calculation of how the stars evolve, we are assuming that the core of the star is not changing and the mass is being shaved off of the outer layers. because we always know the core. We can find the mass just by taking the original mass and then removing some of it according to how long the star has been evaporating. And then we can use the stellar structure model to calculate the new radius, which we can then use together with the new mass to calculate the new mass loss rate. And then we can repeat this process to see how the star moves around in this parameter space. What trajectory will it have? And actually, the trajectories are pretty constrained because the core mass is constant. So they will always move on these lines of constant core mass that have been plotted here. So really what this integration will do is determine where the stars ends up. Does it go all the way down or does it stop very early? It will tell us how it's moving along this trajectory. We evolved the stars for around 3 million years. This is because we know that the activity from the black hole was a few million years ago. So that is the sort of maximum timescale during which we expect this process to happen. Otherwise, it would be irrelevant for solving the problem of missing stars. And we see that even stars below this line that should take more than 3 million years to evaporate actually do experience a significant loss of their mass, since this is about 1/3 of the original mass. So to conclude, we have shown that the radiation from the active black hole at the center of the galaxy can ionize hydrogen and deposit energy efficiently in the atmosphere of the star. And then we have shown that photoevaporation is possible by calculating the rate at which mass is lost from the stars. And a fraction of these stars will be significantly impacted by this process. So we determined that this process can be responsible for some of the missing red giants, and it is likely that it's responsible for this together with all the other processes we saw at the start. Now, to verify exactly at which distance from the black hole or exactly how many stars this could account for, we will need to do more detailed calculations. First of all, one would need to use a more accurate stellar structure model by solving the real stellar structure equations. And next, one would need to run this on a realistic population of stars. And after doing that, then one can actually answer the question, what would be the observations if this model was true? And then they can compare the result with the real observations to determine whether this can be a plausible explanation for the phenomenon.